Welcome back to our Chem 152 video series. In this video, we'll go over how to write a rate law for a reaction. Our reaction for this video is 4A plus 5B yields C, and we have a set of concentration data. We've run the reaction 3 times at different starting concentrations of reactant A and reactant B, and we have some data for the rate of formation for compound C, our product. Our first question asks, in reaction 1, what are the rates of disappearance for A and B? To answer this question, we'll start from our rate of formation of C. We're given that the rate of formation for C is 1.1 times 10 to the negative third molarity per second. We'll write that down first. If we want to find the rate of disappearance for A, we'll start from our data for C. We're going to use stoichiometry to get out of C and into A. From our reaction above, we can see that 4 pieces of A are used up in every time we run the reaction, and we make 1 piece of C. So we'll write that we'll make 1 C by using 4A. However, because we're using up A, we'll say negative 4 for A. This shows that A will disappear as C gets made. If we put this information into a calculator, we'll get that our change for A will be negative 4.4 times 10 to the negative third molarity per second. If we do the same thing for reactant B, we still start with 1.1 times 10 to the negative third molarity per second of C, but now we're changing from C and going to B. In the reaction above, we have 5 pieces of B. However, since they are on the left, we are using them up. Therefore, we'll say negative 5. Since we still have 1 C, that still goes on the bottom. If we do the math, we'll get negative 5.5 times 10 to the negative third molarity per second. This will give us our rate for B. Now that we know our rates for each reactant and each product, we'll find the rate law. To find the order for reactant A, which is the first step in finding our rate law, what we're going to do is look for 2 reactions where A changes, but B does not. If we look at reaction 1 and reaction 2, we can see that between reaction 1 and reaction 2, A does change from point 1 to point 2. However, the B stays at point 1. This is exactly what we are looking for. We're going to use reaction 1 and reaction 2. To find the order, we'll start by calculating 2 constants. The first constant we'll find I'll call lowercase c, and that will be concentration from line 2 divided by concentration from line 1. In line 2, my concentration was 0.2 molarity. In line 1, it was 0.1 molarity. Notice we are not looking at B right now, we're only looking at A. If we divide, we'll get a lowercase c value of 2. We can also find another constant called R. We'll look at rate 2 divided by rate 1. Rate number 2 is in the third column. That is 2.2 times 10 to the negative third. And rate 1 is right above it, 1.1 times 10 to the negative third. If we divide, we'll get 2 again. Now that we have C and R, here is how we determine the order. If R is exactly 1, the reaction is 0 order. Specifically, I want to mention that it's 0 order in reactant A. This doesn't tell us anything about B, and we'll handle that in the next step. If C is the same as R, that means you are first order. Again, this is only true for A, we don't know B yet. And if R is equal to C squared, that means you will be second order. If we compare our answers for C and R, we notice they're the same, and so this reaction will be first order for reactant A. Now that we know the order for reactant A, we'll do the same thing for B. We're going to locate 2 lines where B changes, but A doesn't. Line 1 with line 2 will not help us here, so let's look for another pair of lines. If we look between line 2 and line 3, we can see that between line 2 and line 3, B changes, but A stays the same. Therefore, line 2 and line 3 should be the lines that we use. We'll look at C and we'll look at R. C will be now concentration in line 3 divided by concentration in line 2. Now we're not going to look at A anymore, we'll just look at B. Concentration number 3 is 0.2, and concentration line 2 is 0.1. If we divide, we end up with a C value of 2. To get lowercase r, we'll look at rate 3 over rate 2. Rate number 3 is 8.8 times 10 to the negative third, and then rate number 2 is 2.2 times 10 to the negative third. If we divide, we'll get 4. So first we check if r equals 1. We can see that it doesn't because we got 4 as our answer. We'll check if r equals c. Notice that r is 4 and c is 2, so that's another no. But if r is equal to c squared, which if we look at our numbers, r is 4, c is 2, and it is true that 4 equals 2 squared, which means we are second order for B. Now that we have both of our orders, we can write the rate law. To write the rate law, we begin with the word rate, and we say this equals lowercase k, the rate constant, times the first reactant, times the second reactant. Our reactants are A and B. However, we'll also take those reactants and raise them to their powers. Since A was first order, A is also first power. This means we don't have to write a power for A because if we write no power, that means first. We know B is second order, which means B will be second power in our rate law. So we'll put a squared on the B. Now that we've written the powers, what we'll need to do is fill in all of the data. We have a rate because we can just use the rate from the first line. We also have A because we have A in this position, and the B as well. We'll place all of the values in the correct positions. The rate will be 1.1 times 10 to the negative third equals our unknown K times our A concentration, which will be 0.1 molarity, times concentration for B, which is also 0.1 molarity, and it will be squared. If we do the math on the right side, we'll end up with 0.001 K. And on the left, we still have 1.1 times 10 to the negative third. Now just divide both sides by 0.001. If we put this information into a calculator, we'll get that the rate constant K is just 1.1. So this is how we write a rate law and solve for the rate constant. Also, it doesn't matter which line of data you use. Reaction 1, 2, or 3 would have been fine here, and I just picked reaction 1 for my data arbitrarily. Thank you for watching. We'll see you again soon.